Hi, once again, my name is Monica Lund, and I'll be talking about the ALUM Crystal Lab. This is the last of 3 videos tracking the progress of my BIOS alum crystal growth, and it has been a little over 5 weeks since I performed the experiment. This large crystal and small crystal appeared the day after the recording of the second video. The crystals are transparent. The large crystal is in the center of the vial, while the small one is growing on the edge. Much of the water from the solution has evaporated. The environment my single large crystal grew in was for the most part dark and cold, as the lights in my room are usually low and the temperature no more than 70 degrees Fahrenheit. However, although I have a large crystal, it isn't necessarily high quality because there is some cloudiness at the bottom of the vial, and there is a second smaller crystal. In order to produce a higher quality crystal, one could grow it by seeding, which is taking an already formed small crystal and placing it in a saturated solution. This would provide a foundation for more molecules to attach around. The seed crystal is already at equilibrium in comparison to the saturated solution. Equilibrium happens when the rate of dissolution is equal to the rate of crystallization. D-spacing is a crystalline solid's fingerprint. Understood through the X-ray diffraction method, D-spacing describes the distance between planes of atoms. In this diagram, each blue circle is represented as an atom, and the gray line represents the plane that it sits upon. D-spacing gives insights on how individual crystals are formed. Bragg's formula relates D-spacing to other quantifiable qualities about a crystal. Bragg's equation describes the scattering of a crystalline lattice for a given compound. Using X-ray diffraction, we can calculate the D-spacing for the most intense peak in the diffraction pattern. We have some known values to plug into the Bragg's equation that can help us calculate the D-spacing. So we know that n equals 1 because we're being asked to find the most intense peak. Then from the data that was given to us, we know that the wavelength is 0.015418 nanometers. And then also from the graph, it shows us that the chart is in 2 theta degrees. So whatever we calculate or whatever we find the highest peak to be, which is this one right here, which I determined to be 20.7, you have to divide that by 2 to actually find theta. So you plug all of this information into the equation, and then you can solve for D, which is 0.429 nanometers. And that would be our D-spacing for alum.